Have you ever wondered what it takes for a machine to not just mimic human movement, but to truly feel and anticipate the world around it? Well, welcome to this explainer. We have reached an absolutely critical inflection point right now. Classical control theory, high-frequency optimization, and generative AI, they're no longer separate fields. They have fully converged into this unified paradigm of physical intelligence. So today we are unpacking the algorithmic brain of humanoid robotics. Let's dive right in.
For decades, we were used to robots that were essentially just stiff, pre-programmed machines. They moved from point A to point B because a human sat down and hard-coded that specific path. But how do we evolve past that? How do we engineer a humanoid that can dynamically react to its environment, recover from a violent push, or seamlessly adjust its footing when it unexpectedly slips on ice? The answer is replacing all that rigid code with dynamic, real-time calculation. To give you an idea of the sheer scale of computation we're talking about here, just consider this number. While earlier systems really struggled to coordinate even a single limb, modern GPU-accelerated frameworks have completely shattered those limits. We can now compute optimal, centralized trajectories for up to 16 complex legged robots simultaneously. And get this, all in less than 25 milliseconds. It is a truly staggering leap in agility. Okay, so here is our mental roadmap for this algorithmic stack. We're going to start with Section 1, reflexes via whole body control. Then, Section 2, foresight through model predictive control. Section 3, adaptability powered by deep RL. And finally, Section 4, fine motor skills and dexterous control. Let's start with Section 1, reflexes or whole body control. Think of this as the robot's spinal cord. It acts as the foundational torque resolution layer, treating the humanoid as a single dynamically coupled system, and it operates at a blazing 1,000 hertz just to keep the machine upright. So, with 1,000 calculations happening every single second, how does it handle conflicting goals? It uses what's called prioritized task hierarchies, which are solved through quadratic programming. Priority 1 is pure survival. We're talking balance, torque limits, maintaining ground contact. Priority 2 is motion, like moving its center of mass. And priority 3 is postural aesthetics, like, say, gracefully waving an arm. Survival will absolutely always override aesthetics. Now, you might be wondering, how does it actually enforce those priorities without the math totally breaking down? The secret sauce here is a concept called null space projection. This is a mathematical technique that essentially guarantees a lower priority task will only be executed in the null space of a higher priority task. In plain English, it guarantees a robot will completely ignore a command to wave its hand if executing that wave means it's going to lose its balance and fall over. Like I said, survival always wins. But the real world is messy, right? What happens when the ground unexpectedly just isn't there? In these late collision scenarios, collision-aware whole-body control acts as an instantaneous reflex. It immediately switches objectives via a decision tree to maintain stability. It's basically the robotic equivalent of your heart skipping a beat when you misjudge a step on a staircase, but somehow catching yourself instantly. All right, moving up to Section 2, foresight, model predictive control. If that previous layer was the reflexes, this layer is the cerebellum, planning future movements at roughly 30 to 50 hertz. Think about this quote for a second. Imagine running on ice. You don't just react to slipping, you anticipate it. MPC is this receding horizon optimization technique. It simulates the robot state roughly 0.5 to 2.0 seconds into the future, finds the absolute optimal ground reaction forces, executes only the very first millisecond of that action, and then instantly recalculates the whole thing. But simulating a 30-degree of freedom humanoid into the future that fast requires some clever shortcuts, specifically reduced order models. The linear inverted pendulum model, or LIPM, is lightning fast because it basically treats the robot as a flying brick, just a point mass on a massless leg. It's incredibly fast, sure, but it completely ignores angular momentum. On the flip side, single rigid body dynamics captures 3D orientation beautifully, but it demands a massive amount of compute. Historically, these predictive solvers just completely choked on CPUs. But moving the math to GPU accelerators using platforms like JAX, that has changed everything. By leveraging primal dual ILQR solvers, we achieve logarithmic scaling. This gives us real-time trajectories for multiple robots at once, navigating totally unpredictable terrain with mathematically provable stability. Which brings us to Section 3, adaptability. deep reinforcement learning. This is the cerebral cortex, and it takes over when the world is simply too chaotic for clean physics equations. Instead of humans manually writing out equations, DeepRL lets the robot learn by trial and error in massively parallel simulators, like NVIDIA Isaac Lab. The robot discovers its own emergent gates to master parkour, climb stairs, or recover from violent pushes. It can train incredibly robust policies in a matter of minutes, stuff that would literally take weeks of trial and error on real hardware. However, there is a massive catch here, the sim-to-real gap. The difference between a pristine, perfect computer simulation and our noisy physical world can cause an AI to fail completely when it's actually deployed. So to bridge this gap, engineers rely on 3 vital steps: domain randomization, actuator nets to model the specific friction and quirks of real-world motors, and automatic reward learning. Let's look closer at domain randomization. During simulation, engineers essentially send the AI to a brutal robot boot camp. They actively try to confuse it. They randomly change ground friction, vary the robot's mass by up to 20%, simulate motor wear, and even inject random latency delays. This intentional chaos forces the neural network to develop genuine, rugged, real-world robustness, rather than just getting lucky in a perfect environment. We're also seeing this huge shift away from handcrafted heuristics toward automatic reward learning. Engineers no longer have to manually write tedious rules like give the robot a point if its foot is flat. Now, using bi-level optimization, the framework autonomously infers the absolute most efficient way to walk all on its own. All right, the final frontier, Section 4, fine motor skills and dexterous manipulation. Because it's one thing to balance a heavy bipedal machine. It's an entirely different universe to teach it to delicately pick up a fragile tool. To achieve this, researchers are actually borrowing concepts from the AI systems that generate digital art. We're moving toward generative diffusion policies. Much like how an AI image generator starts with a screen of static and iteratively denoises it into a clear picture, these policies start with random noise and iteratively denoise it into a highly precise sequence of feasible physical robotic actions. Now, managing the entire body at once is just way too complex, so systems use a hierarchical approach. This is brilliantly illustrated by the refined DP framework. It uses the diffusion policy as a high-level strategic commander, dictating exactly what the hand should do and the overall base velocity. But it delegates the gritty, high-frequency details of, not falling over to a dedicated low-level reinforcement learning controller. The results, they're honestly incredible. Consider frameworks utilizing visuotactile convergence, like the finger-eye system. By embedding miniature cameras directly into the fingertips, the system gets a continuous stream of implicit stereo depth and tactile feedback. Combined with precise rotation matrices, the robot can seamlessly detect contact and successfully grasp something as impossibly thin as a piece of paper. So let's pull the whole picture together. What you've explored today is not just a random collection of isolated science projects. It is a completely unified paradigm of physical intelligence. We have the 1000 Hz reflexes of whole-body control, keeping the robot standing. We have the 50 Hz foresight of model predictive control, anticipating the terrain. And we have the high-level, adaptable AI of diffusion policies and reinforcement learning commanding the overall mission. It all stacks together perfectly into one complete algorithmic brain. Which leaves us with a pretty wild thought to take away. For years, AI was sort of trapped behind our screens, writing text, generating images. But as these massive foundation models merge with the advanced physical control stacks we just explored, how close are we to true humanoid generalists? Machines that can step right out of the factory and seamlessly into our completely unstructured everyday world. The algorithms are already here. It's really no longer a question of if, but exactly when.